Hi all, my name is Mike Gargano. Today I'll be talking about the LEAF dataset for my final project in DA5030 from the UCI Machine Learning Repository. So from this page, we can see we have 340 samples, 16 attributes, and is a classification kind of problem. So the LEAF dataset consists of these 40 species. In the actual dataset, there's actually only 30, so I think some of these got removed out for some reason. But the features for this data set are derived from the images themselves. So things like eccentricity, which is how circular the leaf might be, or like average contrast, average intensity, all things that can be pulled from images. And so the goal is to predict the species given all of those features. Um, And this might be very important. Maybe if you wanted to make an app, which I believe it already exists, but what you might be able to do is, given someone takes a picture of a leaf, you want to be able to tell them what is the species of leaf that is, or what species of plant that is, which is a really, really interesting machine learning problem to me. So what we could do is go ahead and just load in our data set. It didn't come with any columns, so we'll go ahead and add those in. And it doesn't look like any of our features are categorical. They're all, besides for our predicted variable, they're all continuous. And so the first thing we want to do is kind of just do some exploration, around the data set. And so what we could do is take a look at this pairs plot, which is going to tell us a little bit about all of our features. It gives us a nice scatter plot, a little bit of correlation, and this histogram on the diagonal that could tell us about some skew. And what we see is definitely some skew among our features. We also see some highly correlated features as well. So let's take a look at what features might actually be skewed. And to do that, I say, give me the max of the column divided by the min of the column. And if it's over 20, well, we should probably transform these values. And we could see that some columns, like the maximal indentation depth, average intensity, and smoothness, they're all pretty skewed. So we'll have to deal with that later on. So from that previous plot, it's very hard to see correlation, in my opinion. So what you can do is create this correlation heat map that really gives you a good picture. And what we see is these highly correlated variables, positively correlated variables, and some that are highly negatively correlated. And so we'll have to go ahead and take a look at how we're going to deal with some of these collinearity problems. I didn't have any missing data values. But we do see some extreme outlier values, for example, 19 there, in aspect ratio. And so what I could do very quickly is just look at the box plots. And I mean, we just tell right away, right? The mean is down here, and we've got these extreme data points out at the top. So we're going to have to deal with that as well. So the next step would be to split our data into our training and our testing, and I wanted to do about an 80-20 split. From the data partition, though, in some cases, what we would see is that the data was not being stratified properly across the categorical variables. So I wanted to ensure that would happen. So I kind of wrote my own little stratification function, also leveraging some of the code here from Stack Overflow, but I had to modify it a bit to just get me the IDs instead of returning me the entire data set. So I can go ahead and just load that function in. And what we see is that it stratifies pretty well, 82% across, and we see that there's no missing values in either our training or our testing set. They kind of both have a little bit of each, ideally 80% into the training set and only 20% of each categorical variable into the test set. So we can go ahead and do that. The next step would be to handle our skewness and our outliers. And from those skewed columns we found earlier, I just created a quick histogram, and you could see that unskewed example. And then after looking at each of the features that were skewed from the skewed columns, what I'm able to do is actually apply the different transformation functions to see which one worked best on each of the skewed. So each of the skewed columns. So we could see that in some cases I used the log, and in some cases I used the square root in this example. And so we can see after we transform it, it follows more of a normal curve, which is exactly what we were looking for. So the next thing is to do, we want to standardize, we also want to standardize it. So we want to have a mean 0 and a standard deviation of 1. So we can go ahead and do that. And it looks like now we have these nice mean 0, standard deviation of 1 features. And we also want to remove skew on our testing set based on the parameters from our training set. That's a very important, aspect of doing skew. And as well as we want to do the same methods for each column that we did as well. Otherwise, everything's going to be all out of whack. So we can go ahead and do that. We're going to take a look at our PCA. So we want to look at feature selection here. And we want to see, since we have those highly correlated variables, it might be beneficial for us to use the principal derived features from the principal component analysis. And we want to make sure we do these two separately on the training and testing set, because we don't want any information leaking from our training set into our testing set here. And because that would kind of over optimize some of our models. So from the scree plot, we can see that the first 6 principal components comprise of almost 90% of all of the variance. I would probably choose 6 as the cutoff here, as there's not really a big drop from 6 to 7. And we could definitely see that it's 96% actually from PC1 to PC6. So we'll use those values. And just a really quick visualization of PC1, PC2, we could see some of the species are separating here, which is nice, but ideally we would see a majority of these separate. That's okay. So the models that I choose to use were KNN, the random forest, and the SVM. These are really the most prominent classification models, and random forest and KNN don't do well computationally for large data sets, but in this case I have a really small data set, so I think it's okay to use these ones here. We're going to use K-fold cross-validation for all of these. So what we can do is predict our PCA loadings for our test set. This is very important. Otherwise, you're not going to have the same columns for the test set. So we can go ahead and do that. I also pass in a train control value here, which basically says we're going to use repeated cross-validation. We want to do 10-fold cross-validation. We want to also do that 5 times and then save the prediction. So we can train our KNN model here. What we get is a 63% accuracy, or it looks like just about 64% accuracy on our cross-validation set, which is okay. It's not great, but it's also not the best that we can do. Let's take a look at some of the cross-validated accuracies out of our random forest. And it looks like we get a very good, or at least better than our KNN model for our cross-validated accuracy, about 67%. Not too bad, definitely not overfit in my opinion. So let's go ahead and take a look at the SVM model. So SVM, again, using cross-validation, had about a cross-validation error of about 31%, which is about 69% cross-validation accuracy, which is higher than the 2 previous models. So that's good, and I don't think it's enough to where it's overfit. So the next thing we can do is go ahead and take a look at how it looks on kind of unseen data using our testing set. So our KNN had an accuracy of about 63.7%. We can know this because we can construct a confusion matrix to compare. And we see that we can just predict, and then from our true values, from our predicted values, get this kind of gigantic table and compute how the accuracies work out. So 63.7%. On our random forest, we have 72.4%, much better increase from our KNN model. So a top contender here. Let's see how the SVM worked out. Very well, 77.5% accuracy, better than our two previous models. So, I mean, if I was going to choose a model here, I would definitely choose SVM. It had a really good cross-validation accuracy, didn't seem to be overfit, and had a really good. It generalized very well over our data set and had a nice 77.5% accuracy on our test set. So the next thing to do was to create an ensemble model. For the bottom tier models, I chose our two best performing models, which are the random forest and our SVM model. And what we do is we basically just take the training predictions from our cross validations and use those to train our KNN model, which is going to be our top level model here. And after doing that, which I can run really quick, we see that we have a cross-validation accuracy of about 63.2%, and the kappa value, which is like an adjusted accuracy, has about 61%. So a little bit less than what I've liked, and actually performed a little bit less than all of our models in the cross-validation stage. But let's see, maybe it'll generalize well over our testing set. Let's see how well it does. Looks like from the testing set, we were able to predict that it had about 65% accuracy, so a little bit better than the KNN model on the prediction, but not as good as our SVM prediction. And this is probably because we don't have many models on the first layer. If we had a few more models on the first layer, it would probably perform a little bit better as a stacked ensemble model. And so from this, I think I learned that PCA is a very important step in kind of making sure you have removing your skew and your correlated variables. I think that was really cool to work through on a data set that I just haven't seen before. So thank you very much for watching, and have a great day.